Okay, so we are happy to have Willie Rush Lim from Stony Brook tell us about a priori bounds and degeneration of Herman rings.
All right, thank you, Peter. Can everyone hear me clearly? Yeah, all right. Thank you very much for the organizers for allowing me to speak here today. I want to talk about a priori bounds and degeneration of Herman rings. So the main motivation of what I'm going to talk about today really is the following. So if you have a rational map, suppose you have a Herman ring for this rational map, you can deform the complex structure, meaning you can deform the modulus and we twist it a bit, but let's just deform the modulus so that it goes to 0. What happens to it? Does it converge to a curve, or does it converge to something that is not a curve, something uglier? We don't know. But I'm going to talk about this today. Okay, so let's just start with some background. So suppose F is a rational map of degree D. Recall that if I have U, which is a maximal invariant domain of this F, is a rotation domain if F is conjugate to a rigid rotation. There are two types. If it's simply connected, then we call this a single disk. Otherwise, it's an annulus, and we call this Herman ring. The two are very much connected to each other in the sense that we have this operation by Shishikura. It's a quasi-conformal surgery operation that actually converts one to the other. If you have a pair of single disks of complementary rotation numbers, theta and 1 minus theta, then you can cut along some invariant curve on a single disk, and then you remove the inside for each of them, and then you glue it along this invariant curve. Right? This is a very simplified picture, really. I mean, the quasi-conformal surgery operation itself involves a bit of a interpolation, yada, yada, yada. But in the end, we get a Herman ring, and then on either side of the invariant curve that you cut, you basically get dynamics that mimic both of the single disks you get that you have originally. Conversely, if you're given a Herman ring, you can pick an invariant curve in the middle, and then suppose you can delete the inside of that invariant curve, and then what is left here is just going to be a disk, and then this produces you a single disk. Okay. All right. So now from now on, I'm going to assume that the rotation number theta is going to be of bounded type. So what is this? This was mentioned yesterday by Igors. Basically, if you write theta as a continued fraction expansion with terms A1, A2, A3, and so on and so forth, there is a uniform bound, say B. Okay. And then there's a theorem by Gao Feichang in 2011 that basically tells us that if suppose you have a rational map with a single disk that is invariant, and it also has a rotation number theta that is of bounded type, then this is a quasi-disk, and this boundary contains the critical points. And not only just that as well, here we also know that the dilatation depends on two things. One is the degree D, and also B, which is the bounds in the bounded type assumption. Okay. So the next thing is that, okay, can we say the same thing for Herman rings? We can basically use the Shishikura surgery and basically say that, oh, okay, we actually have a similar statement over here. So every boundary component of an invariant Herman ring of a rational map is also a quasi-circle containing a critical point. There is a bit of an adjustment over here. So the dilatation still depends on the bounds and the rotation number B, and also the degree D. But there's an extra factor that comes to play, which is the modulus of the Herman ring. The reason being is that in the surgery procedure, there is a quasi-conformal interpolation involved, and then the dilatation of this interpolation map will depend on the modulus in general. Okay. So the next question is, can I remove this dependence on mu? Can I remove this dependence on the modulus? Is it actually possible? And the answer is yes, at least for a certain class of maps that I'm going to introduce next. And this is what I'm going to denote by curly h depends on three things, d0, d infinity, and theta. So this curly h is the space of all rational maps F that satisfies the following conditions. The first one is that I want to make sure that they have super attracting fixed points at 0 and infinity of certain prescribed criticalities, d0 and d infinity. Okay. Secondly, F has an invariant Herman ring. I'm going to call it this fancy h over here of rotation number theta. And also, this Herman ring is placed such that it separates 0 and infinity. And then aside from that, we also have this assumption that every critical point of F, every free critical point, so those that are not 0 or infinity, they must be captured on the boundary of the Herman ring. Okay. There is a reason why I introduced the space this in the curly h. This is not unnatural. If you're more familiar with the Shishikura surgery, then I have this proposition for you, which is that this curly h space actually consists of all rational maps that can be obtained from the surgery procedure out of a pair of polynomials, p0 and p infinity, and such that the degrees of these polynomials are d0 and infinity. And then both of these have invariant single disks. And the rotation numbers are complementary, so theta and 1 minus theta. And not only just that as well, I also have the assumption that all the free critical points must lie on the boundary of the single disks. So just a bit of an illustration. What we should think of is something like, so this is a single disk. We have a pair of them. And then we have some critical point on the boundary. So if I draw the p-image, maybe one of them is that. That would be a quadratic. Maybe if you have cubic, it would be something like that. And then the corresponding map F would be something like, we have a Herman ring. And then we have 3 critical points that are free. So one of them is the one inside, and there are 2 of them outside. So this would be, in this case, it would be P0, P infinity, and the map F is this guy, basically. Okay. So there is a reason why I introduced this space. This is basically, think of it as the simplest, class of Herman rings for rational maps that you can think of. And for this class of rational maps, for this curly H space, I can remove the dependence on the modulus. So I have a priori bounds. This is the main theorem, which is that it tells us that the boundary components of the Herman rings of rational maps in this class, in this curly H, they are quasicircles. And not only just that as well, the most important thing is that the dilatation depends only on the degrees d0 to infinity, and also the bound b on the rotation number. It does not depend on the modulus. It does not depend on the modulus. At this point, does anyone have any questions? All right, I can continue. I would not talk about the proof, but I'm going to continue with some of the consequences first. Oh, okay. No. Yep. Okay. So what I would like to do is talk about degeneration. That's the main motivation that I have, that I said earlier, right? So with that, I would like to introduce a new object. What I'm going to call this is what I'm going to call a Herman curve. What this is a forward invariant Jordan curve, such that on which f is conjugate to irrational rotation. But then we also have this optimality assumption that H is not contained in the closure of any rotation domain. Additionally, we call this a Herman quasicircle if we know that it is a quasicircle. So there was a talk on Tuesday by Fei Yang. This is basically the same object. He called this the degenerate Herman ring. There are a few reasons why I would like to use this term and advertise this term instead, Herman curves. So there's a trivial example. Trivial in the sense that there are some Herman curves that we've known for a very long time, and these are simply just a unit circle, okay? Or just Euclidean circles in general. The example that I have over here is a cubic Blaschke product, zeta z squared z minus 3 over 1 minus 3z, and the zeta is the unique number in the unit circle such that the unit circle itself is a Herman curve for a certain rotation number theta. So this is the Julia set. As you can identify here, this is the unit circle itself, which is Herman curve. All right. So I guess that raises a question, which is, it was raised by Eremenko 2 years ago at this conference. Can non-trivial Herman curves exist? So as Feya explained on Tuesday as well, it is possible using some cheap tricks, such as we can do a surgery by replacing the super attracting phase point, one of them to be just simply attracting of multiplying non-zero, and that breaks the symmetry. But then the combinatorics along the Herman quasicircle will still contain the symmetry. So there's still a bit of a information carried from the Blaschke product. But is it possible for me to produce more examples, those that do not have the symmetry from the Blaschke products? And the answer is yes. So I'm going to go back to the curly H space that I introduced earlier. And I'm going to talk about degeneration. So when I say degeneration, it means that I want to look at what happens when the modulus goes to 0, right? And for me, what I can do is I can consider this limit space. I can take the closure of curly H and delete the curly H itself, lying within the space of rational maps of fixed degree. I'm going to call this curly H boundary. Just to note that this is not really the boundary of curly H, simply because curly H is not open inside the space of rational maps. So that's why I put the boundary up here, not really in front. Okay. So what can I say about this? So by a priori bounds, by independence of the modulus, I can say that every map, every rational map inside the curly H boundary, inside the limit space, it has a Herman quasicircle of rotation number theta. Okay, so that tells us a way to, I think I can find Herman quasicircles from here. This is just a direct consequence of a priori bounds. However, it doesn't really quite tell us whether or not the curly H space actually exists or not. Or I mean the curly H boundary. It tells us the property, but it doesn't tell us whether it exists or not. I guess before talking about existence, I have a little schematic diagram over here. So this is what you think of really. It's suppose you have a Herman ring. In this diagram, this is D0 is equals to 4, and the outside is equals to D infinity is equals to 3. And then this is reflected by the pre-images. We see 3 inner bubbles over here, and then only 2 outside. And then as you deform the modulus goes to 0, then what we should expect really is a Herman quasicircle. So this is just a quasicircle with pre-images. It's going to be 3 of them inside, and then 2 of them outside. So yeah, existence. How do we answer that? So let me deviate a little bit and talk about slightly something that is slightly more technical. So suppose I take F in the curly H boundary, right? So it has a Herman quasicircle, and then I'm going to endow this with the combinatorial metric. What this is the pullback of the normalized Euclidean metric on the linearization of F. So you can think of this as the normalized metric on the Herman quasicircle that is invariant under the action of F itself, under the rotation. So the combinatorics, so whenever I say combinatorics, it means that this is the data consisting of the criticality as well as the relative combinatorial position of the critical points that are found on the Herman quasicircle. And then the criticality over here, there's a slight subtlety. Okay, so if I have a Herman quasicircle like this, and then suppose I have just one critical point over here, and then maybe the pre-images are going to be like that. So this is degree 5. Okay, this is it has different combinatorics compared to this one. So the point I'm trying to make is that when I say criticality, there's an inner criticality, there's also an outer one as well. And in this case, it's different. This case is going to be 2, 2. Well, sorry, D0 is 3, D infinity is 3. In this case, D0 is 2, D infinity is 4. All right, so another theorem I can say is the following. So given any prescribed combinatorics, I pick any combinatorial data that I like, whatever it is, there exists a rational map in the curly H boundary that realizes such combinatorics. Now this one, the second theorem is somewhat an application of a priori bounds, and I can give you a sketch of what the proof looks like. So the first ingredient is Thurston type result for Herman rings. Basically, this is a result by Xiaoquang Wang in 2012, 10 years ago. And it basically allows us to pick Herman ring, say F1, that lies in the curly H space, having a Herman ring of some combinatorics similar to the chosen one, right? And then from this F1, I can perform quasi-conformal deformation. So I would like to get the modulus to be close to 0 as possible. So formally speaking, I can get a normalized family, say FT, with the same combinatorics, but then the modulus of the Herman rings go to 0. And then the last ingredient is the first theorem, which is a priori bounds. And then with a bit of some analysis work, basically this implies, well, this gives us enough compactness for me to find the limit, right? So there exists some F inside the curly H boundary such that FT goes to F subsequently. And then with that as well, F carries the combinatorics that I want. And this gives me the rational map that I desire. Okay. So this theorem also guarantees the existence of any, I pick any combinatorial data that does not carry the symmetry in the critical profile of Blaschke products, right? So I can produce lots of examples of non-trivial Herman rings. So I have 2 examples over here. So if people are falling asleep, hopefully you guys are more excited by pictures. The first one, this is a degree 5 rational map, right? And this formula does not come out of nowhere. This is designed such that it fixes 0 infinity with criticalities 2 and F4. And it also fixes, it has one free critical point at z equals to 1 in blue over here. And then the C value here, this is the critical value. And I picked it so that it has a Herman quasicircle. And then here, the orbit of 1, I denote it, I call it red over here. So this is the Herman quasicircle. And then you might guess that, oh, basically the pre-images of this, you can somewhat see it already. There's one of them here inside, one in the bubble, but there are 3 of them outside, right? So there's, asymmetry in the critical profile at z equals to 1. And for that reason, this is something that you can't produce out of Blaschke products. This is a non-trivial example of a Herman curve. And then another example over here, this one is, this formula over here is a cubic rational map that was first studied by Xavier Booth, John Milner, and Araceli Bonifat. So the 3 of them worked on this cubic rational maps that has the property that it commutes with the antipodal involution of the sphere. And as a side note, Q over here, there's a Q bar. So this is it's not a conformal, a parameter space. It's not holomorphic. It's just smooth in general. And then within this, cubic rational maps, this parameter space, you can actually find a wealth of examples of Herman rings. In fact, the ring locus itself within the parameter space has positive measure. So it's not difficult to find Herman rings over here. And then I can study the limit points of this ring locus, right? When I look at the limit points, I can find one parameter Q that such that the rotation number is golden mean. And then that produces me this example, right? So this is, if you can see 2 blue dots over here, this one and that one, those are the critical points, and they are antipodal opposites on the sphere. attached over here is an outer bubble, this one. So that's the pre-image of the Herman quasicircle. And then this one is, there's an inner bubble over here attached. So this one as well is also a non-trivial example of a Herman curve. Okay. Another thing I can say is that basically the two of these, you can think of it as a amalgamation of single disks for this one. This would be, you can think of it as a welding between a quadratic single disk and a single disk of a degree 4 polynomial. If you don't like the term welding, maybe you can call it mating, or I don't know which one is better. Okay. All right. So all of the results that I mentioned earlier rely on the first theorem, which is a priori bound. So how do I actually prove this? I'm just going to give you a rough idea on how I prove it. So suppose H, I pick one boundary component of the Herman ring. I call it H, and I'm going to endow it with the combinatorial metric. Okay. And then I'm going to pick an interval, the little interval in H of sufficiently small length, say less than 0.1. And then I'm going to call 10i the enlargement of I by 10 times. Okay. And then this enlargement is such that it has the same midpoint. It has the same midpoint as I. And then I'm going to call, so this quantity is W10i. This is the extremal width of curves connecting I and H minus 10i. So you have I, and then you thicken it 10i, and then you consider the complements. So I have a little diagram over here as well that tells you what the extremal width should actually tell you. So if you're not familiar with extremal width, this is the reciprocal of the extremal length. Okay. So if the Herman, boundary H is fairly nice, its dilatation is fairly low, then you should expect that the W10i to be small in general. But then if otherwise, then in this example for over here, then there might be some I, some little interval that captures the near degeneracy as a quasicircle. And in this example, then the W10i will be very large. So what am I trying to say over here? So to prove a priori bounds, to prove independence of the modulus, it is sufficient to find some upper bound k such that every sufficiently small interval I satisfies the following inequality that W10i has to be bounded above by k. And again, k here is important that k has to be independent of the modulus. So it only depends on the degrees and the upper bound b on the bounded type condition. Okay. But what I would like to do instead is go by contradiction. So our goal is reduced to showing the following theorem. So this theorem tells me the following. So suppose there is an interval that is sufficiently small length, right? Sufficiently short. And then it has width, so W10i at I over here is sufficiently large, say greater than k. And then there is another interval. So from I over here, you can find another interval of, again, sufficiently small length, but then the width, the W10j, is going to be at least twice the W10i. And the fact that I can control the length over here allows me to run the inductive arguments, apply this theorem infinitely many times. So I get a sequence of intervals along this H so that the W10, the width over here, exponentially increases. And with that, it gives me a contradiction, right? So from a local near degeneracy at I over here, it gives me a local near degeneracy at other intervals, but the near degeneracy over here exponentially increases. All right, so the proof of this, it requires the near degenerate regime package. So many of our steps are inspired by the following three papers. This one is by Jeremy Kahn and Michal Lubitsch at 2005 on quasi-additivity law and covering lemma in conformal geometry. And then also by the work of Jeremy Kahn in proving a priori bounds for infinitely renormalizable quadratic polynomials of bounded primitive combinatorics. And then there's also a recent work by Będlewo and Michal Lubitsch on proving uniform a priori bounds for pseudo-Siegel disks for quadratic polynomials. And then in the last two papers over here, there is an analogous formulation of the following theorem, really, some kind of amplification theorem. And then in the work of Będlewo and Michal Lubitsch as well, on their Siegel disks, they also use the vocabulary, which is the W10 quantifiers here. All right. So instead of giving you the proof of the theorem, which is going to be quite long, so instead I'm just going to give you some of the differences and the complications that arises in our setting in the Herman rings. So the main challenges here are the following. The first one really is, I think this one should be quite obvious, which is that both sides of the Herman ring are non-trivial. In the sense that if you look at Siegel disk, for example, then one side of the Siegel disk is just pure rotation, right? So secondly as well, there's also a lack of positive entropy. So positive entropy here was used by Jeremy Kahn in the context of primitively renormalizable quadratic polynomials, and that gives you some advantage in analyzing the width after some sequence of branch coverings. But we don't have that over here, and we have to adjust it in different ways, really. And then thirdly as well, we also have that intervals in H are not perfectly invariant under F. So you know that this is irrational rotation. There is a first written map, but it's going to be adjusted by a little bit. And this is in contrast with the little Julia sets that arise in polynomial-like renormalization. Right. And then lastly as well, I also get to deal with arbitrary number of critical points and combinatorics. So that's basically it that I want to say. Oh yeah, there's one last thing. I'm gonna close with this last slide, which is gonna give you guys a series of open questions. The first one, which I think is a spirit of the series of talks today earlier. I guess my talk is incomplete without mentioning the word house of dimension. So if F lies in the curly H boundary, so F has a Herman quasicircle, is it true that the house of dimension of this Julia set is 2? Is it also true that maybe the Lebesgue measure of the Julia set is 0? Unfortunately, we don't know. I do think that the both of these questions are the answers are positive. It seems like it would be 2 because if you zoom near the critical points, you would not. There are no porosity that is evident on the picture, at least numerically. Okay. And then secondly, as well, can we also describe this, limit space when theta is of unbounded type? So based on the talk that we saw by Fei Yang, well, we see that we can actually get smooth Herman curves for certain conditions, right? So in particular, he did such when theta is of high type. And then thirdly, with this, a notion of Herman curve that I introduced, there is a reason why I just call it Herman curve and not degenerate Herman rings. And this is why, because I don't know why, I don't know whether this question is, there's an answer to this question or not. So it's a limit of degenerating Herman rings, always a Herman curve. And then lastly, is every Herman curve a limit of degenerating Herman rings? So that's kind of like the converse of the previous question. Okay. For number 4, I do believe that this should be true at least when theta is of bounded type. I have a partial answer for this. For the space of rational maps that I've considered so far, this should follow from combinatorial rigidity. And this is still a work in progress, still have written. So basically with combinatorial rigidity, plus the second theorem that I mentioned earlier on existence theorem. This will give me the answer, the positive answer for number 4. Okay, I think that's basically all I can say today. Thank you.
Okay, thanks for the talk, Willie. Are there any questions?
Thank you. It was a
Willie.
great talk. Oh, sorry. Go on.
Okay.
Oh.
Yes, go ahead.
Hi, Wee. I'm Fei Yang. So
Hello.
I have a question. Hey, hello. So you consider the case when the critical points are all on the boundary of single disks. If some critical points are not on the boundary of single disk, what can you say about your result? Is it still true?
So you're saying that if there are critical points, free critical points that are not, the free critical points are not on the boundary. So I haven't. Yeah, sorry.
Yes.
Yeah, so I haven't looked at that yet. I do believe that it should be true, but I think the analysis is going to be a lot harder. Yeah. So yeah, I'm not entirely sure yet.
Okay. Thank you. Very nice talk. Thank you.
Okay, Lasse.
Yeah. So thank you for the talk. It's really, really interesting. I'll start with a question about your pictures, which are beautiful. So how do you find your maps? Is it that you start with something with a Herman ring and then you sort of just degenerate, and because of your situation, you know that you'll end up? But
are you talking about this rational map?
Yeah, this one.
No, so I don't start with Herman ring because that's quite difficult in general. Finding Herman rings is quite difficult. But what I start with is just the condition that this rational map fixes 0 and infinity with criticalities 2 and 4. And then I also have a critical point at equals to 1. And then with that condition alone, it just gives me this rational map reading. It's not difficult. I also have a formula for arbitrary criticality. So if B0 is maybe 2022, for example, and the infinity is maybe 10, then I also have a similar formula. And these numbers don't come out of nowhere. They are from Pascal's triangle somehow. Yeah. And then also, I guess another thing I can say is that from rigidity, it will follow that C here will be unique.
Yeah.
Okay.
Okay. Well, maybe you can tell me a little bit more about that afterwards. Okay. So you mentioned that you said your techniques are inspired in particular by the Kahn-Lubitsch quasi-additivity law, which makes sense because you're looking at these extremal widths.
Yeah.
But since you said it's inspired by, so do you have to do something? So you don't use this quasi-additivity law directly?
I do.
You do. Okay.
Do.
So you apply it directly.
I do.
Okay.
Yeah.
All right. Thank you.
Question.
Great talk. Thanks. Thank you very much. So my question is for this key theorem when you control how you degenerate. So if my understanding correct, what Dima and Misha did, it was for arbitrary rotation number.
Yes.
Well, and
arbitrary rotation. Yeah. Uniform a priori bounds.
Yeah. And what doesn't go through in your setting for arbitrary rotation number?
That's a lot more difficult. So what Dima and Misha did is that they introduced this term called pseudo sigil disks. And what they do is that from sigil disks, you fill in the fields. I do feel like I can do such an operation, but it might raise more complications. This is something that I have in mind to do in the future. But the complications are such that, you have fields that you have to fill in from the outside and also the inside as well. And there might be more complications. So maybe I can answer that in 3 or 5 years. I don't know.
Okay. Yeah. Looking forward. Thanks.
Okay, if there are no other questions, let's thank Willie again. The next talk will be in 2 minutes.